In this example, we will anti-differentiate the proper rational function 2x squared minus x plus 4 divided by x cubed plus 4x. Because this is a proper rational function, we can just jump immediately to the partial fraction decomposition. So looking at the denominator, we can factor it as x times the quantity x squared plus 4. So the form of the partial fraction decomposition will correspond to the linear term x will be a over x, and then corresponding to the irreducible quadratic x squared plus 4, we need to balance it out in the numerator with a bx plus c. Now that we have the form of the partial fraction decomposition, we take this denominator on the left and we multiply both sides by it. So we'll be left with a 2x squared minus x plus 4 on the left. On the right, we will have a times the quantity x squared plus 4 plus bx plus c multiplied by x. Now, the first step here is to plug in any intelligent choices of x that will allow us to immediately solve for one of our constants. And corresponding to any linear term, we will always have an intelligent choice. If we plug in x equals 0, we can solve for a. So if we let x be equal to 0, we end up with on the left-hand side a 4, and on the right-hand side a times 4. So we know that a is equal to 1. Now in order to solve for the b and the c, we will simply expand algebraically on the right. In terms of x squared, there are a plus b of them. In terms of linear terms, there's a cx and a constant term 4a. And the only way these two quadratics can be equal, on the left-hand side it's 2x squared minus x plus 4, is if all of their corresponding coefficients are equal. So we really do have a system of equations that we're working with. The coefficients of the x squared term tell us that a plus b is equal to 2. Looking at coefficients of the linear term, so we would have a minus 1 is equal to c. And lastly, comparing coefficients of the constant term, we have that 4 on the left is equal to 4a on the right. So 4a is equal to 4. So as we saw above, we already know that a is equal to 1, c is equal to minus 1, and we have that b is equal to 2 minus a, which is going to be 1. So we have now solved for the unknown constants in the partial fraction decomposition. Now it's time to anti-differentiate. So recalling what we had on the previous slide, this will be the antiderivative of 1 over x plus the antiderivative of x over x squared plus 4 minus the antiderivative of 1 over x squared plus 4. And writing down these antiderivatives term by term, the first antiderivative is the natural log absolute value of x. For the second antiderivative, you can either just write down what the antiderivative will be, or you could use a substitution. So here you could note, if we let u be x squared plus 4, du is 2x dx. So we would need a 2 on the top, so a 1 over 2 out front. And I will let you fill in a step of work here. This is 1/2 natural log absolute value x squared plus 4. And for the last antiderivative, let me just recall for you the formula, a common anti-differentiation formula. 1 over x squared plus a squared, its antiderivative will be 1 over a, arctangent of x over a plus c. Looking at the form of our integrand, 4 is 2 squared, so a is equal to 2, and this will be 1/2 arctangent of x over 2, and then plus c, because it's an indefinite integral.